Dr. Bapi Chatterjee for doing that.
Am I audible without using the microphone? Is it okay? Yeah. Everyone on the back?
Yes, sir.
Yes. Because okay, am I audible to people joining online? Yes.
Yes, sir.
Okay, perfect. All right. So yeah. So I am supposed to, or rather, I was supposed to, take two sessions today. One was an introduction to machine learning and deep learning, and the second one is optimization for machine learning, training, machine learning models, so to say. Now because the event has been running a bit behind time, that's totally okay because it's first day. So what I would do rather is that I will perhaps keep my first part a bit shorter, right, introduction part, because I believe that anyway, many of you already have either studied that formally in a course, or maybe you would have done that, explored that out of your interest. So I will keep this part short, and then the training machine learning model part will be sort of focus of my talk. Alright. So before I could start, let me take stock of the kind of audience. So how many of you have taken a course in machine learning in your program? That we take it. Yeah. Machine learning, proper machine learning course. Okay. Alright. So it's it's not majority. It looks like, right? But that's okay. And how many of you have explored machine learning out of interest? Let's say end-to-end course or some other online thing. Yeah. Okay. So that is roughly like 50% or a bit more than 50%. So there is some proportion here of audience who are still to perhaps see a bit structured introduction to machine learning. Let me try to do that. Okay. So those who have done a course in machine learning have you can explore it by yourself. Will find things very easy, right? Maybe at a very basic level, but that's what I was supposed to be doing, a general introduction to machine learning. That's what it is mentioned on your schedule. Alright, so let me then go into the technicalities. So why learn, right? What exactly do we mean by learning? So for example, I mean, we understand clearly that there is no need to learn, computing maybe someone's salary, right? So that's not a learning process. So learning, but learning is now at the sort of center stage, right, of entire exploration, computer science, electrical engineering, even other basic sciences. Now they are being based on learning. So learning is used, right, when human expertise does not exist. For example, no one has ever done any navigation on Mars, so maybe we don't need machine learning for doing that kind of task. Similarly, there could be areas where humans are unable to explain their expertise. For example, just think about it. So when I am speaking, maybe after a while, if I speak again, you would know that who is that person who is speaking, right? Similarly, your friend, you even without looking at the face, you know that who is speaking, right? Just by the speech. Okay, but can you explain that how exactly that happens? Identifying someone just by speech, right? So we have that expertise that we can identify people by just their speech, but we cannot explain that how that happens. So their learning is used. Okay, there is an entire area of machine learning for speech, and then solution needs to be adapted to particular cases such as biometrics, right? So biometrics is one thing where that you need adaptive solution. I mean, one can perhaps let's say, biometrics that also includes face recognition and so forth. You can have different angles and so forth, right? And that entire thing cannot be stored. You cannot store infinite number of samples of someone's face, right? So there, the solution needs to be adapted, and there you need actually machine learning. So these are the basic, why exactly machine learning? So machine learning is roughly it can be defined as, although I mean perhaps this is by a definition by someone So machine learning is a study of algorithms that improve their performance, right? And the performance is again targeted at some task, right? For example, face recognition could be a task, and that performance improves with experience. Okay. So entirely, so mathematically, this is like a tuple, so to say, right? PTE together make a machine learning algorithm. So if someone asks what is a machine learning algorithm, you should define it in this way. This is a bit more formal. Okay. All right. So what we mean by learning again, learning. When we say learning, right, machine learning in particular, so we are learning general models from data of particular examples, right? So there is data and there is model, right? In this, okay. So laser does not work on this one.
It not work.
Laser does not work. Okay. Very interesting. All right. So in course, you have models, right? When we say models in machine learning, they have very specific meaning. You should know that. That will become clear. But so there is a very famous quote here that models are in general wrong, but some models are useful. This is from a statistical model, right? So the models, the machine learning models that we develop, we cannot certify its correctness, but many a time they are useful, and that's what it is happening. Anyway, so data is cheap and abundant. We have lots of data generated almost every second. Lots of images are being uploaded to social media. Lots of quotations, quotes are being shared. On again social media, Twitters and so forth, and they are actually generating data. So there is data volume, so to say, flood, right? So for example, whenever you are doing some kind of retail transaction, you are purchasing items and so forth, that is generating data. So data generation is like, so perhaps in terms of speed, that could be ranked at the top, right? The data generation speed. So what we do in general is that we build a model that is a good and useful approximation to the data, right? So we fit a model to the data. All right. So at this point, after having given this much, let me try to get a definition out of our intuition. How should we define a model for machine learning? Model for machine learning. Right, so look at the last line, right? So we are saying that build a model that is good and useful approximation to the data. So essentially we are saying that fitting a model to data. Those who have done any numerical analysis course from mathematics background or maybe even engineering mathematics course, you would have seen that data fitting is curve fitting, data fitting is a topic, right? So at the end, what happens? You actually give your answer in terms of some parameters, right? A, B, C. For example, a model could be ax square plus bx plus c, right? A, B, and C are the parameters. So you should know it, very precisely. This is again a very popular question in machine learning interviews. What is a machine learning model? What is the difference between a model and algorithm in machine learning? Right? So a model is a set of parameters. That's its formal definition. A set of parameters. Right? Okay. So that set of parameters by which the model is generated is sort of developed, and then you fit it, right? And then that fitting process is called training. That we will sort of do after the introduction. So we talked a lot about data, right? Data is available. Data has generation has speed and everything, right? So there is another study topic, right, which is called data mining. And you should also have clear understanding that machine learning is different from data mining. What is data mining? So data mining, alternatively, it is also called knowledge discovery in databases, KDD. Okay. So this is a non-trivial process of identifying valid, novel, and potentially useful data. So most of the time, right? Let's say if you are recruited in the industry, right, as a data scientist. So believe me, you won't be doing machine learning most of the time. It's just data science, the data mining part, right? So I don't know, you would have heard maybe when it is like I don't know package of 8 to 10 lakhs, right? For data scientist roles. Most of the times you do SAS or Excel based data analysis, so that is data mining. You just sort of mine the feature, useful feature of data. Machine learning is a bit different from that. Machine learning, is kind of where you will be actually applying those data mining tools to learn some model. So model learning is at the center of machine learning. Model creation and fitting is at the center. Okay, so applications of data mining, market-based analysis, people do it all the time. Customer relationship management, CRM, and so forth. Credit scoring, medical diagnosis, all these are data mining, job roles in a way. Machine learning, on the other hand, is a study of algorithms that improves their performance over time, right? At some task, the tasks should be defined precisely, and that should come with experience. Okay, and there is a role of statistics, role of computer science. Role of statistics is in terms of sort of giving a precise mathematical sort of foundation to these models. And role of computer science, as you know, that these are the computer scientists who have made made it possible to have all sorts of discoveries in science these days, with high performance computing, with cache optimization, with multiple nodes doing together distributed sort of computing. Okay, so with that, this is again very how to say, at a high level without any technicality involved kind of a discussion. Okay, so going forward, machine learning, there are lots of categorization, paradigms, terminologies. If you just search this term machine learning on Google and then go to Wikipedia, you will encounter all these terms, right? Some of them are just new terminologies, and every day you have perhaps new terminologies popping. So I would go to details, but I believe that all of you have at least seen, if not have studied it more formally. Supervised learning, where you do classification, right? Cat versus dog, or maybe car, truck, bus, and bird, right? So there is multi-class and classification, two-class, multi-class classification. Regression or prediction, where let's say you have been given some data of, let's say, Andrew scores, so to say, right? You have house rent data, right? How many rooms are there in a house, and what's the distance from the city center, what should be its rent. So that's prediction. And then unsupervised learning, mostly clustering. So suppose you have data from, let's say, a locality of people, and then you have to cluster them in high income and low income, middle income kind of group. That's clustering. There is a third distinct category of machine learning, which is reinforcement learning. In this talk, I won't go into unsupervised and reinforcement learning, but we'll define them very briefly in the following slides. Supervised learning and unsupervised learning, they have been sort of hybridized in a sense to come up with semi-supervised learning, where you have let's say, so supervised learning is also where your data is labeled. So your data has some kind of class, right? For example, cat image, dog image, and so forth. So that is called a label. And then if you have some labeled data, some unlabeled data, then what you do is that first you train your model on the labeled data, and then the unlabeled data gets kind of clustered in over the learned model. That is semi-supervised learning. Self-supervised, where you generate data. It was also a bit discussed a bit in the morning. There is rule-based machine learning, which is AI, which Professor Singh talked in detail about, right? Rule-based machine learning, which is precursor to today's machine learning. Okay. And then these are like newer terminologies, automated machine learning, right? Where you just apply some algorithms, you develop some algorithms, and then do most of the machine learning related developments automatically. There comes reinforcement learning. Auto machine learning or automated machine learning, auto ML, sometimes people call it, is where you apply reinforcement learning to improve the machine learning algorithms. By the way, if I'm speaking a bit fast or anything is sort of not clear, please feel free to interrupt me at any point. I'm very happy. Meta learning, learning about learning, right? So meta, maybe you would have come across this term in metaphysics. So you just throw this term meta to any topic, and then it is like sort of going one level higher, right? So meta learning is learning about machine learning, how machine learning algorithm is sort of doing, learning about its dynamics. That is meta learning. Adversarial learning, from where you have this GAN or generative adversarial network, and then LLMs finally, where because you do not have enough data, so you generate some data and then sort of improve your learning. Then online learning, where data is coming in sequences, data is not available altogether. Batch learning, data is coming in batches. Continual learning and lifelong learning, again just changes in the definition. So these are some terminologies. So please keep in mind, this is gentle introduction to machine learning. I am not going into detail of any of those. First, taking supervised learning, we have classification tasks. So for example, let's say here we have an example that we have some data for sort of savings and income, right? Income versus savings. So we have two-dimensional data here, right? And then we have a classifier. So you can see this blue, line, sort of curve, right? This is piecewise linear curve. I hope that those who have familiarity with mathematics, you can see that this is piecewise linear. So this piecewise linear curve actually sort of classifies it into two domains, right? Where discriminant classification is also known as discrimination, right, in machine learning terminology. So if income is greater than θ1 and savings is greater than θ2, then then we call then call it low risk, otherwise high risk, right? So for example, people in banking and credit card industry keep on doing this kind of classification to classify some customers into high and low risk domains, so that they could accordingly offer or not offer credit card of some particular credit. This is classification example. Some applications are face recognition, character recognition, speech recognition, medical diagnosis, web advertising. Let me just skip over them. Face recognition, for example, is another classification. In fact, the most well-used, the most explored, classification application of machine learning, which is face recognition. Regression, more formally, it is generating a model G here, right? G based on the parameter theta, right? And the data x, right? So your data is given, parameter is given, and G is the model which is fitting here. So for example, here you can see you have a linear model there, right? Linear model, and then data is in form of input x and its label y, and the parameters are w and w0. So this is prediction regression model. An application, right? So I believe all of you have heard of self-driving cars by now, if not have seen it. So this could be perhaps one application of regression in self-driving cars. So let's think over it. So what is happening here? Your coordinates are given in form of x and y, right? Now what happens? Let's say when you drive a car, then based on some coordinate, you decide whether you should go left or right, right? I mean, as you drive on road, right? So every location, every point of your sort of driving path can be given in form of coordinates, right? Now at some particular coordinate, you decide whether you should go left or whether you should go right or you should go left, isn't it? Similarly, let's say if you have just I don't know, maybe some of you have used those self-moving mops, right, in home, isn't it? And they have this kind of technology inside. So what happens is that they have to decide based on some obstacle which direction they should go. So you can think about an application of regression here. So based on a particular coordinate, you have to compute the angle of movement, isn't it? So whether your mop should move left or right at 90 degrees, or it should keep on moving, things like that. So this is like let's say when your xy coordinate is here, it should actually move in the direction alpha 1, this obtuse angle, right? Otherwise, maybe if it is here alpha 2 and so forth. So this is like a very preliminary application of regression in that setting. But of course, it involves a lot more engineering than in self-driving car than just this very basic coordinate-based angle prediction. So I hope everything is fine up until here. One particular model that I would like to discuss. Very sort of, so I chose to include this particular model in my discussion because as I see the presentation lineup right over these 4 days, you have diffusion models perhaps scheduled for tomorrow, then you have generative models, then you have other CNN sequence models as well, right? Which others are going to talk. But decision tree, I really like decision tree. So believe me, I mean, in industry, if you are working in machine learning, right? If you ask people in industry, they would say that even if your neural network does not work, right? Decision tree always works. It works from image to finance to speech to all sorts of scenarios. Decision tree is very interesting machine learning model. In fact, now there are sort of research papers coming out. I believe there was a very recent publication that for tabular data, which are the cases where neural network actually outperforms decision tree, right? I hope you are getting the point what I'm trying to make. So decision tree has been a de facto model for many cases, including tabular data, right, for machine learning. And now people are researching that why and where a neural network should work better than decision trees. Okay, so having said that, okay, so just a very quick, very brief, definition, so to say, of unsupervised learning before I go to decision trees. Okay, so unsupervised learning is what normally happens. Usually you have no output, so you just have, let's say, in terms of clustering, if you have data clustering, so you just have clustered centers, right? It does not output as such any parametric model that we just saw in supervised, in case of supervised learning. Other applications such as data summarization, association analysis. I'll again talk a little bit about association analysis. Customer segmentation, CRM, right? Customer relationship management, color quantization, image compression. So these are like examples of unsupervised learning. So this is association learning, right? So I talked about rule-based learning. On Wikipedia and other places, you will find that association-based learning or learning associates is classified as a classical method of AI, which is rule-based learning, right? But many places it is also classified as unsupervised learning. What happens? So, so I believe that all of you have done at least basic probability, right? And you understand what is conditional probability, isn't it? Because that's the minimum thing, to understand machine learning. So probability of y given x, that is probability that somebody who buys x also buys y, where x and y are products or services. That is called so that's sort of a type of or let's say a particular use case of association-based learning, which is basket analysis. So based on these things, what people do. So I believe that you can think about your supermarkets, right? Let's say you go to this Reliance Mart and so forth. So you would always find that some kind of items are put together, right? So they do machine learning, behind that. People actually collect data, and then from time to time things are also shuffled. Like let's say if someone buys, I don't know, maybe some kind of clothes, then maybe shoe rate would be closer, things like that, right? So that's basket analysis. If someone buys X, then what is the probability that Y will also be purchased? Okay, reinforcement learning. So here you have this terminologies. Policy, right? Policy is something based on which again you take decision. Okay. So for example, all of you have heard that now computer-based chess engines, they beat human players in it. So that's a very a prominent example of reinforcement learning, where of course chess as a game was implemented much before. It was totally rule-based, but now it has become more and more reinforcement learning. So it improves, depending on the policy that it has to take. So again, it does not have any supervised output, but delayed reward. So based on the reward, it will improve the policy. I'm not going into the detail of reinforcement learning, but just know that most of the games that are now in the market, machine learning based games, they actually use reinforcement learning. Even your LLMs, right, have used this technique called RLHF. How many of you have heard? Reinforcement learning using human feedback. Right? So what is happening is that when we are using these models, right, then many a time they also ask us to give feedback, right? And those feedback are incorporated to improve it. Okay, decision trees, as I said. So decision tree is a model, right, that defines the hierarchy of rules to make a prediction. Okay, so maybe some of you have seen it, but let's see. So for example, body temperature. Let's say based on body temperature, we decide, if it is warm, then what is the possibility that it could be mammal, right? And if it is cold, then of course it is non-mammal. Then if it is warm, if it gives birth, then it is mammal. If it does not, then it is non-mammal. So this is like a very sort of toyish example, but this is a case for decision tree, right? Ultimately, what is happening? You are taking decision, right, to figure out something. Okay, so tree. I believe that all of you have seen that in your data structure course. So this is exactly that. You have root node and then internal nodes and then leaf nodes. Right? So root and internal nodes have test rules, and leaf nodes make predictions. Okay, that's the decision tree structure. Decision tree learning is about learning such a tree from labeled data. So because it is labeled data-based, model, then what exactly is the category of decision tree? Supervised, unsupervised? Supervised. So decision tree is supervised learning. Okay, so I'm not sure whether you can see it clearly, but in any case, so suppose you have loan approval prediction to do. Okay, I think I should not even touch this one, otherwise I get it out. Anyway, so based on the age and ID, and then whether someone owns house and so forth, let's say a credit card or maybe a bank has to decide whether loans should be approved or not, right? That's the application use case. The basic idea is very simple, right? So recursively partition the training data into homogeneous region. What do we mean by homogeneous? So yes, any question? Okay, all right. So partition the data into homogeneous region. What we mean by homogeneous? I think you can intuitively see here that maybe here those dots, right, or those circles which have same color, they are homogeneous. Okay. So what are you supposed to do? You are supposed to draw lines, partition the regions such that circles of same color are together. That will be homogeneous. So let's say we first draw one line like that, a vertical line. After that, we draw two horizontal lines. This is a space partitioning, in particular binary space partitioning, and then we like that, and then that, and then it is kind of quite homogeneous. Okay, so you can again think from here that with that kind of partitioning, what will happen? You can have a hierarchy of sort of regions, and that gives you a tree, which is decision. Yes. So these are like homogeneous regions that we get out of. So by the way, I must also mention that where exactly we are getting the data from. This is multi-dimensional data, right? So each of the data points are sort of coding, those details, those features that we just mentioned in the previous page. So here is a homogeneous region. We'll have or a majority of training inputs with the same or similar outputs. So based on the label, we will have homogeneous. So majority should be. I mean, you can also call this particular region homogeneous because majority has same label. Within each group, get a simple supervised learner example given to predict the majority label, right? To make a decision. Okay.
आप सब में से किसी ने ऑनलाइन ज्वाइन नहीं किया है, प्लीज़ मेक श्योर कोई भी माइक ऑन नहीं है, एनीबडी ऑफ यू हैव ज्वाइन.
Alright, sorry for that interruption. So decision trees, because it is supervised learning model, right? We agreed on. So therefore, it should be used for both regression and classification. Let's first see decision trees for classification. So here we have features. Okay, I think. Okay, so there was one more label here. So this is feature 1, let's say on x coordinate, and feature 2 on y coordinate, right? So these are like 2-dimensional points. So what we are doing is that we are creating a decision tree, right? And then we start partitioning. Start with partitioning, let's say along the x1 axis, right? So this is x1 axis, the horizontal axis. So if x1 is greater than 3.5, then it is like one branch of tree. If it is less than 3.5, then it is the other branch of the tree, right? And then based on yes and no, you have branches of tree. Again, once you have these 2 branches, you partition it further and so forth, right? So you see, once we have reached here, right? Now there is no more partitioning needed, right? And then we can predict, label. Predict its label, whether it is red or green, so it is red clearly, right? So then based on these values of x1 and x2, given this particular data set, right, we can predict whether its color is red or green, right? So here we have already reached the leaf level. Next is that this is predict red is given. Predict green is also done, right, in a similar way, that now that region does not have any red ball. On the other hand, this region has both red and green ball. So what we should do is that we should draw another line. Right? So that was not working. The same line which we had at true, that was not working. So here we have actually now x2 decided by whether its value is greater than 3 or. and now we have perfect labeling, right? So decision tree is done, and then prediction can be done perfectly, and then you can classify. So when I'm saying prediction of the label, it is like multi-class prediction. So well, I mean, I hope that you would understand. If not, have read it for So discrete regression is classification. Okay. Continuous classification is regression. That's kind of So when I'm saying prediction, if it is like in a discrete setting, then that's classification. So here we have like discrete classes. Okay. So then root node contains so decision tree is sort of property. Root node contains all training input. Each leaf node receives a subset of training. By the way, do we have some way to ask if there is some online question?
Yes. You can ask.
Okay.
They are already
Right, but I believe, okay, we can see the chat, pop up. Yes, right, yeah, I think it's fine. Yeah, so please feel free to ask if you have any question, right, online audience. And the way will be that you just post your question or maybe raise your hand, one of those, and then I will get that. Okay, so root node contains all the points, right? And as we go down the hierarchy in decision tree, the number of points are lesser and lesser, and at the leaf node, it's homogeneous set. Okay, let me. Okay, so so idea I believe is very simple and very effective as well, and now you understand what is happening, right, at the level. So some considerations: what should be the shape, size and shape of the decision tree, in particular number of internal nodes, number of leaf nodes, branching factor of internal nodes, depth of the tree, right? So I'm not going into describing overfitting, but I believe some of you are familiar with that idea. In any case, so overfitting of any model is such that given the training data, your model is so well trained on the training data that if some test data comes, its accuracy actually drops on the test data, right? So the same goes with decision tree. Its depth should not be so large so that it overfits. So you should always keep that in mind, right? So some test data, so if it is like fully, then it could be like, okay, think it like this way. So if you have too much mixture of these points, right, labels, and then at the end what happens that your leads just contain a single point, what will happen? It will be like totally overfitted, right? Then anything that comes, you will have wrong prediction, isn't it? So that should not happen. That you should keep in mind, right? A branching factor. So I believe that in your data structure course, beyond binary trees, binary search trees, some of you would have seen multi-way search trees, k-array search trees, so to say, right? Anyway, so then you can have different branching factors. For example, in B tree, you can have a higher branching factor than just 2. Okay. Depth of the tree will depend on branching factor and your sort of decision of how much in depth you should go. So these are some considerations. And then split criterion at internal nodes. Notice that. So in the just previous slide we saw that when we were sort of trying to partition one of the space by x equals to 2, it was sort of not giving us perfect partition, right? It would have then taken us to maybe one more level of creating hierarchy. So therefore you should have a proper sort of search of these places where you should partition this, right? So there comes your hyperparameter search, so to say, for decision trees. Okay, so some of the points that I can, So split criterion at internal nodes. If your classifier is not working, let's say optimally, then you should change the classifier. So at the end, to figure out where to sort of partition, it depends on choice of classifier. Okay. Let me skip this one. I think the idea is clear. So there is a concept called entropy related to decision tree. So how many of you have ever heard this term entropy in computer science in particular, beyond physics? Physics, I believe that all of you have in your class 12, studied second law of thermodynamics, entropy. So entropy in computer science. Anyone? Okay. So cool. So look, when we speak, right? Or okay, let me give a bit more funny example. So many a time it might have happened with some of you at least, right? That you filled up that entire 32 pages your answer sheet and you got maybe 2 marks, right? So what happens exactly in that case? So that's actually low entropy example, right? So entropy is the amount of information that a particular set carries. Okay, so the set of characters or set of words that you filled up in your exam sheet that did not have much information, maybe you would have just done repetitions. When we speak, right? So sometimes people just speak things out of turn that has low entropy, right? Which is not even needed. So similarly, on the other hand, in decision trees, low entropy gives high purity. Okay, so think it like this. So what will happen? If you have low entropy essentially means a lot of repetition, right? So if you have a lot of repetition, then as you take the decision, you will have high purity. If you have high entropy, then there will be a lot of mixing of labels, right? And therefore purity will not be possible if you don't want to have overfit. Are these things making sense, right? Otherwise, what will happen? Your leaves will end up having a single, label, and it will be overfitted. That we don't want, right? So low, entropy, that means high purity in decision tree. Okay. All right. So more or less, that's what I have in decision trees. Please keep that. Okay, again another example, but that's okay. Okay, now decision trees for regression, decision trees for classification we saw, decision trees for regression, right? So let's say x is greater than 4. So here we have again 2 coordinates, x and y. X is greater than 4. Then let's say we go to one branch of the tree. If x less than 4, then we go to the other branch. Now what will happen? That all of them, maybe here is a prediction model. So all of them that are greater than 4, they can be fitted with one line there, right? So that's like a small linear sort of. So okay, think it in this way. Let me explain it this way. Instead of showing this one. Okay, wait a second. So let me explain what is exactly happening in regression. Suppose you did not use decision tree, what would happen? I mean, my problem is that my cursor is not working. Let me. I think even that much is not. Let me just. Okay, I hope that should work. So suppose you did not use a decision tree, right, for regression. What would happen? If you did linear model, right, for this particular data, maybe your line will be somewhere here, isn't it? Yeah. If you did, let's say, polynomial regression, right? Polynomial regression. So, well, I mean, similar to line is like, in your coordinate geometry, you have static lines and then curves. I think polynomial regression, maybe second order polynomial, that would predict something like that, right? And then as you get new data point, that the prediction will not be as clean as perhaps when it could happen here, right? So now you see, based on your decision tree, you can reach here, and now you have a line which is almost touching each of them, right? So this is like a much better regression, isn't it? So what you have done, although you are doing linear regression, right, at the end, at the leaf levels, but before that you have actually imposed one decision tree. So decision tree is helping you in regression as well, right? So I hope idea is fine now with you that decision tree is actually a very interesting model which can actually amplify your other sort of basic classifier or regression. Okay. All right. So summarize some key states of decision tree. These are simple and easy to interpret. right? Nice example of divide and conquer. Divide and conquer, the basic algorithmic paradigm. Application of divide and conquer in machine learning, and easily handle different types of features. It is very fast at test time, right? I believe that by now you would have understood that at test time you won't have to do large calculations as perhaps you may have to do in polynomial regression or neural networks, things like that. But here it is just logical, left, right. So again, test performance is quite fast. And then the most important application of decision trees is to coming with decision forest. So how many of you have heard of this thing called XGBoost? Gradient boost, XGBoost? Yeah? Yeah, maybe you can come across this term. So XGBoost, the de facto based accepted, most well-known model in industry, XGBoost. So that is decision forest. You make ensemble of many decision trees, and that gives you decision forest. Okay. So it is used in several real-world ML applications, recommender systems, gaming, Kinect. If you have used, in that also decision trees under the hood, right? Human body for human body pose estimation, but it has some weaknesses. In particular, learning optimal decision tree is NP hard problem, right? It is intractable. It is unlike your standard maybe linear regression or logistic regression for regression and classification. It is very much a discrete problem to solve, and then therefore this is NP hard. And most of the existing algos are greedy and heuristics. Okay, so therefore it can sometimes become very complex unless some pruning is applied. So that is about decision tree. So because other lectures won't have decision tree as particular this model described. So I hope that this is a good piece of information for your experience in this workshop. Now from here, let me move to. So up until here, it was machine learning, so to say. Although you saw that some depth was coming, right? With decision trees, we actually went into depth, right? Beyond linear regression. But it was still not deep learning. For whatever reason, people don't classify decision trees into deep learning. What is deep learning? Deep learning building block is something called here, neuron, right? Alternatively, it is also known as perceptron. Very simple idea. You have a single classifier here, right? So you have sort of some input signals. We call them traditionally we call them signals x1, x2, and so forth. You can also call them input data, right? Input signals. You apply some processing, maybe just summation, very simple summation, and then the output is y. Many a time those input signals have different priorities, different essentially different weights. You have to assign different weights. So this is weighted sum, okay? And then you have output, right? Now even going further, before the output you apply a function, right? This is called transfer or activation function, and that gives you a single neuron model. With a single neuron, if you sort of stack them together, you come up with a layer. This is neural layer, right? It's still a single, a stack of single neurons. Okay. The same way, the input weights will be sort of sent out to all the neurons, or maybe multiple neurons in the layer, and that gives you a single layer neural network. And as you stack those layers further, it becomes a neural network, right? And as the network depth grows, it becomes deep learning, right? So for legacy regions, decision trees, irrespective of their depth, they are not classified as deep learning. On the other hand, deep neural network are. So in this workshop, you will come across all sorts of application-oriented or domain-specific neural networks. But in my following talk, I will talk in particular about training neural network. Although you have seen the system aspect of training neural network, quite nicely, I should say, in modern stock, right? But I will talk a bit about its theoretical side. But before I leave, neural network zoo, right? Maybe you can also, maybe you have seen it on internet before, but here is the source. So this is very interesting sort of display of various neural networks. So you have different kind of cells, right? And based on those cells, first you have perceptrons, then perceptrons make feed-forward network, and then you have something called RBL, radial bias network, and so forth. Deep feed-forward network, like I just showed, that multiple feed-forward networks. As depth grows, it becomes deep feed-forward network. The source is mentioned over here. You can just go and check out. This is very interesting sort of collection of figures for sort of descriptive display of different neural networks. So I mean, at most we have heard, maybe even in our machine learning course, about CNNs, convolutional neural network, then recurrent neural network, and so forth. But the the space is much bigger, and it is in fact growing. Okay, so every other year, if you just watch the space of new neural networks, so people are coming up with all sorts of neural networks. And in particular, in this workshop, you will be taught about generative adversarial networks, this so-called GAN, and yeah. So after showing you this neural network review, before I sort of stop this particular this talk session, let me for our information just put it here. What is generative AI, right? So this is workshop on generative AI. Generative AI at its core is something called generative adversarial network. Okay, what is generative adversarial network? It is actually a setup of two neural networks, two actually generative models. Two models, right? These models could be neural network. These models could not be neural networks. That's totally fine. Okay. One of them will be called generative model. The other one will be called adversarial model. Okay. So what happens? Generative model is one that generates data following joint probability distribution. Okay, so if you have labeled data, then it will follow the joint probability distribution Px, probability of x and y together. Otherwise, if it is unlabeled data, it will have a probability of only x. So following some distribution, you can generate data. How can you do that? So I mean, what happens when we say that? Okay, first of all, distribution, right? I hope distribution is fine with everyone. This is probability distribution. We are not talking about any other distribution, not distributing anything. It is probability distribution. All of you have studied probability density function, right? And cumulative distribution function. So essentially you draw those histograms and frequency curves, and then what happens? So once you have those histogram and frequency curves, based on that, just put select one point from there. So you have to first learn that curve, right? That frequency histogram and frequency curve, and then on from that curve pick a data. That will be called generating a data from a given distribution. Okay, everyone fine with that idea? Probability based. So first you learn the distribution, the joint distribution, and then pick a data from that distribution. Send that data to another model, which is adversarial model, right? This is a discriminative model. Okay, this is generative model. The other one is discriminative model. It has to do classification, very simple binary classification, whether your generated data is from the desired distribution or not. Okay. So you generate the data and send it. If your adversarial network is able to classify this data correctly, right? When you are generating, it is not coming from the original data, isn't it? Then your adversarial model should say that no, this is not from original data, isn't it? Now, so if it is not able, then it just learns, right? Because it has seen new data, it will learn. Okay, this was not from original distribution. Maybe when you send it from the correct distribution, then it will say that no, this is correct data. What will happen? There will be a two-party game. So Professor Singh was he just started with game theory. I believe he just mentioned game theory. So this is actually two-party game, right? And he actually mentioned that why AI people learn game theory. This is that application of game theory in machine learning. And then there will be a state where your adversarial model will say that yes, generated data is from the original distribution. So once that state is reached, both your generative model and adversarial model have got trained, and that is generative model. Yeah. Okay. And you are going to see all sorts of applications of generative AI in this workshop. I leave it here. Okay, or maybe we can take a short break, and then I can come back, or should I continue?
Yeah, you can continue. We have break at 4.
Okay, perfect. All right. Okay, sure.
So meanwhile you can ask the questions. Actually.
Yes, exactly right. Yeah, I was
Because
a lot of
this
information.
was the important topic which he has covered introductory part, but you should ask some questions also.
Yes. Yeah. Any question? Everyone fine with what is happening here in the model? Be clear about the terminology: model, algorithm, right? And generative, adversarial networks. Any doubt?
Even you have small questions you can ask, because in further lectures we were not able to understand that those terms.
Okay. So, well, I believe that it was very simple, right?
So someone has typed something.
Please in manage.
Please ask her. पूछ बोलो सर. On the speaker on the speaker and
Yeah.
the speaker on the
Generative model forms a bit of regression or
Yes, that is a regression, and the other one is classic. This is predictive. Very good. Okay, cool. So, with that, let me move to my other.
I
yes.
have a question.
Yeah.
Sir, basically, like here in GAN, Generative Adversarial Network, basically we create synthetic data, right? And sir, we have one concept in like data
Self-supervised.
augmentation, data augmentation.
This is exactly data augmentation.
So this is also data augmentation.
But with that, what is happening that both the models are being trained. Okay, very good question. So many a time. Is there any other question, or this is?
So this is
okay. Perfect. So many a time, those who have trained, neural network, in particular maybe some RaceNet for MNIST and CIFAR-10 kind of thing, you would have seen something called transform, right? So you apply a transform in your image. So what it does, it actually, so it registers your image, in a way. So based on the transform, what you do is that you don't exactly use the original image, but you maybe sometimes rotate that image a bit, maybe sometimes crop that image a bit, so that you can actually train your model better. You can apply the same transform technique to augment your data, but it is just increasing the data set size. Nothing is being trained over there. Here, along with the augmentation, you are also training both the models. So that's the difference. Okay. So your discriminator, the other model, is being trained to being fooled, right? And that way your predictive model will become better, right, in fooling it. And essentially, what is fooling? Generating data so good so that it is taken as from the original one. So it solves your problem of let's say data scarcity, right? In a more with quality, right? That now your generative model with not just so look, data augmentation could be very simple. So let's say if you have just one-dimensional points, take 2 points and create its convex combination, right? That also is one augmentation, isn't it? You take multiple points, create its convex combination. I believe some maybe you know what is convex combination, right? That also gives you data augmentation, but that is not sort of training a model at the same time. So this is interesting. It is not just augmenting, but also training the model. Good. Any other question? Okay, so that was an introduction to machine learning. Now, yes, training the models, right? In particular, training today's machine learning and deep learning models. Okay. So, I I prepared actually 3 parts of this particular talk, but very nicely the speaker from NVIDIA covered the system aspects. So maybe some of them I will perhaps go over a bit faster. Let's see. So these are the recent advances in machine learning, right? So all these big models, GPT-4, and then GPT-4 is 1.76 trillion model, right? So this is again a kind of modern models, right? Game of parameters. Not only that, tokens. We were talking about tokens in the morning. So this is the kind of number of tokens that have gone into training these models, right? So total tokens. So for example, these are different models. So for example, this Piper model, right? You can see that it has been trained over almost 40 trillion tokens. So this is a number of tokens in trillions. Okay. So huge amount of data, massive amount of data that is being used to train these models. In terms of size of data, right? Again, data set size is huge in not just gigabyte. These are in several orders of magnitude of gigabyte. I mean more than terabyte. And I'm pretty sure that some of you would have come across this term called exascale computing, right? So we are reaching now exascale computing where exabytes of data are being processed. This machine learning training problems. Machine learning ecosystem we just saw in the previous talk. We have roughly supervised learning, unsupervised learning, and reinforcement learning, and then there are some kind of combination, right? So in supervised learning we have regression classification, unsupervised we have clustering and then dimensionality reduction and so forth. Maybe some hybridization thereof, semi-supervised learning, self-supervised learning, right? So in particular, focusing on supervised learning, here is the core idea, right? So you have training data and model, right? Some training happens on big machine, right? Powerful machines. At the end of training, you have trained model, right? You have a trained model, and then you do inference. You just take some unseen samples, those samples which were not used for training the model, right? And then you just execute your model, right? On that test data, and that is called inference. And model, we already said that model is a set of parameters, right? What will happen with set of parameters? Mathematically, once you have a set of parameters, what do you do with that? You create a function, right? So at the end, your machine learning model is a function in form of set of parameters. Okay, so we are going to focus when we are saying supervised machine learning, we are going to focus on training, right? Training part. And I hope that now it is clear that even in GAN, at the end it is training two neural networks if it is sort of a deep learning based GAN. Okay, so model. Let's express this model using this mathematical notation X. I'm lost at not being used my concept anyway. So let's have this abstraction. So our model is a d-dimensional vector X. Okay, everyone fine with this kind of description? So essentially d parameters together, and then we have training data. Let's say we denote our training data by big S and every training sample by little s. Okay. The training algorithm, right, that we apply for training a model, the most popular one is stochastic gradient descent. Okay, I'm not building the theory from gradient descent to stochastic gradient descent, but just know the algorithm at its face. So this is an iterative algorithm. What is iterative algorithm? You do one step of the algorithm, you sort of have the result right from there. So essentially what will happen is that you have a state of the model, right? So your model is a d-dimensional vector. Initially, let's say it has a state x0, right? You do one pass over the data, and then at the end you have, after one pass you have x1. You start from there, do another iteration and do another iteration. So therefore it will be called an iterative optimization procedure. So here is one iteration, right? Compute the loss function. Loss function is, okay. So loss function, idea is that you take the because this is supervised learning, so you have input data and its label. You take a bunch of data samples, compute your model, right? This function, the model is being the function which we obtain from the model is being denoted by in this little f. We compute that, right? And then okay, let me write it. All right, let me do it this way. So I have this a bunch of samples B, our set of parameters x, right? Applying this x and b, we compute O. O is the output function from your model. Okay, O is the output function. With that, you will have some, so this is B. So this is a bunch of samples. For each of those samples, you will have, some labels, right? Yi. So data is this S is essentially xi, comma yi. One sample is xi, comma yi. So because I am using the model as little x, let me use big X over here. So big xi, comma y. Please don't get confused. At any point, if you have any doubt, feel free to ask me. Right. So here we have the parameter. This b, even before b, let me do something like that. X, comma xi minus yi. Right. What happens? So this is output by the model, and this is the actual label of the data. Right. And this difference. You can do something like that, right? So just take, maybe this is a scalar, so even the norm will be, just its absolute value. So maybe that one, okay. So this is a square of the difference between the predicted value and actual label, okay? And sum it up over all I, and that is your function f, okay? This is the loss function. So compute the loss function. I hope to some extent it is okay with everyone.
So can you understand the meaning of model here?
Yes.
What is model? See, sir has written O of x, comma xi.
So I said that this is model, right? And I said that this is O, function, a function. Yeah, so what has happened here?
That was the output of the model.
Can you understand where is the model?
Model is basically the small x,
Right.
where we are feeding that batches of data.
OXI is the output data.
OXI is the output.
So O is the function, right, whose parameters are x, right, little x. So therefore, we apply this function, and this function will be applied over the set of parameters little x and a data sample big xi, right? So take every data sample, compute the function's output, and then find the difference between the predicted output or model based output, so to say, and the actual output, actual label which is available with the data, right? So our data sample is coming as xi, comma yi, right?
Actually, I am asking this question so that they can understand parameter is model or function is a model.
The parameters
So
are
function is the model we are calculating the loss of.
Yes, you should understand that x parameter is representing a model, or function where it is passed, it is a model. You should tell them, you should understand.
simply mathematical function.
Function is a this.
No, so parameter is what constituting the model, and we are updating the parameters. So that way we are updating the model basically. Every time we pass in
I
that
am asking students are getting this thing. Parameter is considered as model or function is a model.
the set of parameters that there is
So
considered.
all of you are getting what some people are confused. Parameter, some people are saying function.
Okay.
So
cool.
function is when you put model dot predict and you get
So
the
can you
output.
please rewrite this equation so that
Sure,
we can
sure,
use it?
sure.
Because I have doubt they are confused. in
Okay,
this
sure.
case.
That's a very good interruption. Very good, point to have some clarification. So what you are saying is right. So the model is set of parameters. The function is parametric function. So what is happening? I mean, you have set of parameters, and the function is parametric function. So function is based on the parameters, right? So when we say model, it is set of parameters. So when we say model function, it is the parametric function. Okay, everyone fine with that idea now? Okay, perfect. So parametric function or model function, so to say. So for example, neural network. So we just saw neural network. Let me draw it here before I move, because neural networks will keep on coming. So what was happening in our neural network? Let's say each of these nodes are what? Just a weighted sum, applied over with some activation function, isn't it? That was every neuron we just saw, and then multiple of those neurons, make some layers, and then we have something like that. This was the kind of figure that we had seen, right? And then we have one more maybe here, right? This is let's say output layer. So what is happening? Let's say x1, x2, x3. These are like actually big x1, big x2, big x3, right? These are like different data input. Now we applied first function over here, which was the weighted sum applied with activation function. Its output is sent to this one, that one, right? Similarly, the output from here is sent to there and there, right? Now these outputs will behave as input for these neurons, isn't it? For these neurons, the second layer ones. Second layer ones, and then that output will go to here, right? Maybe some output is taken from there as well, and then you will apply one more activation function, which is software max manage, I believe many of you know, and then finally you have this output O. Okay, so what is happening? This is at the end, O of maybe say this is layer. Let's say this is layer 2, then layer 2's function 1, then layer 2's function 2, right, 2, 2, and so forth. So this is a composite function. I believe that all of you have known composite function in your class 12. So neural network is at the end just a composite function. Each of these neurons are being represented by what? Its weights. And those who have done neural network in more detail, you know that along with weight you also have something called bias, right? So the parameters of one neuron is weights and bias. So parameter of the entire neural network will be collection of all the weights and biases together. Is that okay? And then the entire neural network will be a parametric function with the set of those weights and biases. Okay. So how many of you have used this MLOps tool called weights and biases? 1 dB. Yes. Okay. So there is this tool called 1 dB, right? Weights and biases. Okay. So as you create neural network, you can, so these are very important tools. Maybe you can note it down and explore it. I don't have time, otherwise I would have shown you. These are very useful things. So as you train neural network, how your model changes, you can visualize it. Okay. So now we have a composite function here, right? At the end, this is parametric function, the model function. And so this loss function is essentially this function, right? This function where we have the difference between the model based output and the actual label, and then some function of that. Sometimes we take this square function. Many a time we take something called negative log likelihood function, but without going into detail of those functions. So this is loss function, right? Loss function is collection of loss at all possible times. Everyone fine with that idea? Yeah. Once you have a loss function, you compute the gradient. So I believe all of you know how to compute the gradient of composite functions. Gradient of composite function. How do you do that? Chain rule, right? Chain rule. Yeah. F of this is what we did, right? H of G of F of X, right? And then you first differentiate H with respect to G, then that with respect to F, and that finally with respect to X. So this is at the end composite function. So in neural network, the gradient computation of loss function is just chain rule, and that is back propagation. So it was mentioned in the morning. So back propagation is nothing but chain rule implemented. Okay. So compute the gradient using back propagation for neural network. Maybe for other models you don't even need to do back propagation, because if it is linear function, very simple one line, one step or maybe gradient computation, and then update the model using this particular update tool. So essentially what you have to do, you have previous state of the model, compute your gradient, right, on a bunch of samples, and then multiply that with a dampening factor. This alpha is a dampening factor. It is popularly known as learning rate, and then update your model, right? So update the model right now. So this is also called, in terms of neural network training, this is called error correction. Okay. Back propagation. Yes.
So basically, like parameters which we are talking about. So in a neural network, we have a number of weights and biases. So that is what we train, right? That is what we update in every epoch.
Exactly.
So parameters is basically the number of weights and biases,
Set of those weights and biases.
and not the features, right?
No, the features are from data, right?
That like xi and yi is the
Those
feature.
big X are data features, right? Big Xi's are data features, little Xi's are parameters.
Parameter, that is weights and biases.
Yes.
So basically, is our parameter a model or parametric function we get as a model? The doubt.
Okay, very good. So
The
the sir had
book says that it is a function, it is a model.
sir had a very perfect interjection here, right? So model is set of parameters. Model function is the function. Output is model function. Take care.
Function will take parameters.
Because function is parametric function. Function is based on parameters. Okay. All right. So, but believe me, some of you have definitely non-zero probability of facing this question in your interview if you happen to be interviewing for some machine learning role. What is the difference between model and algorithm? Okay. All right. And then
General definition of any model is that it takes something and convert it into.
exactly. And recall I said that all models are wrong, but some are correct, right? So that's what will
Many
happen
models
here.
doesn't work.
Yes, exactly. Most of the models don't work. And then this rule, the update rule, iterate, right? And you iterate for sufficient long, for sufficiently a good number of iterations. When do you stop? When do you stop? When when maybe this gradient value becomes small enough so that there is no further maybe noticeable change in your model, right? There you stop. That's very natural idea. This is a stochastic gradient descent. So first of all, there is gradient, right? There is gradient computation. So therefore, gradient based. So what is happening? Descent, right? So just to go a bit more basic, there are three terms: stochastic, gradient, and descent. Okay. So function, as we know, that function can be expressed as these curves, right, or surfaces, right? If it is a high dimensional function, then as surfaces. If it is two dimensional, then as curves, right? You compute the gradient, you maybe compute the gradient over here, and what we are doing, we are minimizing the loss, right? So we are minimizing the loss. If this is loss function curve, then we aim to reach this position, isn't it? So essentially, starting from here, we are doing the descent, right? Descent like that, and finally we are reaching this point. So therefore, gradient descent. Why this stochastic term? Stochastic term because we are picking this bunch of samples. Okay, and then picking the samples happens with following some random distribution, right? So as long as it follows some randomization, you could have called it random gradient descent, but for legacy reason, people call it stochastic gradient descent. Both mean the same, right? Random or stochastic mean the same. So therefore, stochastic gradient descent with stochastic samples. Okay. So I teach that in more detail in my course. I think soon enough you can find my course online on NPTEL, hopefully sometime soon. But otherwise, for now, this is here. Okay. So able training issues, right? So that was the basic SGD algorithm. training is to big data, right? So we just saw that 40 trillion tokens can come in, and then you have to process all that data in one go, in one pass, right? And what will happen with that? The training will start feeling hit, right? So earlier, if you have like a small data, it was okay, but now your training will start feeling hit. Not only that, your model size has also grown to be like a billion parameter model. So this D has become like more than a billion these days. So with big data and big model, your training is even more stretched, right? So it was being said in the morning, right, that even with a BGX machine with 8 GPU so forth, you have to spend like 7 days or something like that. Right? So this is that kind of a situation. Not only that, it is also increasingly the case that we cannot collect the data, in one place. Okay, so we cannot have data centralization. Why? Because of various rules, right? Various guidelines of data collection, data privacy issues, right? So therefore, what is happening? Data is being decentralized, right? So data are being collected at different nodes. For example, so I believe all of you have used Google Keyboard, right, on your mobile phones, right? And now Google Keyboard is very efficient in predicting your sentence, isn't it? So how has that happened? I mean, Google by law is not supposed to collect your, what you are typing. That is your proprietary, that is your private, message and
Patented learning.
Exactly. So that is your private, data. So Google, what it does is that as you sort of install your Google Keyboard app on your mobile, it along with installs a small machine learning model, right, on your mobile itself. And what it does is that when your mobile is idle, when you are not using it, maybe overnight, then that small machine learning model is trained. That's how your battery is sometimes drained, right? And after being trained, they don't sort of communicate your data, what you would have typed, right? What your Google Keyboard would have seen, but it actually sends that model. Model at the end is just set of those numbers, right? Set of parameters. So sending that numbers which does not reveal your actual data is allowed by law, but sending what you have typed is not allowed by law, right? So this is now more popularly called federated learning. This is decentralized data, and you are doing federated learning. So training happens at these small nodes, right? And then all these models are synchronized at a big computer. That is federated. So distributed data, massive amount of data, and decentralized data. These are like big challenges for modern, ML training. So what we do? We apply distributed machine learning. So in the morning, it was said several times that you purchase NVIDIA GPUs and do machine learning training. But although NVIDIA has done an excellent work in terms of giving you a lot of libraries, but still you have to know the tricks of the trade, right? It is not that straightforward that you can just go and maybe take some library-based function of some PyTorch-based function, or even NVIDIA's library functions, and you can train it efficiently. There will be a lot of challenges. So you should know that how to write more efficient modules and libraries in PyTorch. For example, TensorFlow. Okay, so distributed machine learning, I am going to give you three. I'm going to describe it in three parts. One will be systems perspective. Systems perspective, I will go over a bit quickly because a lot of things was already said in the morning. The other will be its theoretical perspective. Okay, and third will be I will be talking about SGD and its friends. Okay, SGD you saw, but there are several variants of SGD which are so I think in the morning it was mentioned on the slide that you can apply Adam optimizer, right? Maybe some of you have heard of Adam, but what exactly Adam is, how exactly it is implemented, what is the algorithm behind? Very quickly I will describe those things as well. So the systems perspective, distributed system. Again, in terms of category, you can have two categories of distributed systems. One is shared memory based. Even your mobiles have multiple cores, right? So your Snapdragon mobile chips, now they come in dual core, quad core, sort of, right? High-end mobiles even have octa-core Snapdragon chipsets. So that is shared memory-based distributed system where the same memory is being shared by all the cores. The other one is distributed memory-based system where you have different computers connected by a communication network. Okay, that is message passing system. Both of them could be synchronous and asynchronous. What is synchronous? Synchronous is a synchronous distributed system. Is that when, let's say, multiple processors, in case of shared memory, or multiple nodes in case of message passing based system, once all of them would have done one step of processing, the next step would be taken only after it is ensured that all of them have done the first step, right? So this is like log step based processing, right? That will be called synchronous processing, synchronous distributed system. And where you don't care about that because of obvious reason that you want speed, right? If some code, let's say in your computer, in your laptop, suppose you have like a quad core based multi-core CPU, if one core has become faster, right, it has done a lot of processing, it's natural that maybe you would assign more tasks to that core instead of waiting for other cores to finish so that you could go ahead, right? So that is called asynchronous model of distributed computing. Okay, so asynchrony can apply to both shared memory as well as distributed memory. In shared memory, cores can have different speed. In distributed memory or message passing setting, you can have different nodes working at different speeds, and then maybe doing their work independently. Everyone fine with what I am saying? Now we are actually coming to the computer science aspect of machine learning, right? Beyond the mathematics and statistics. Okay. So data could be distributed. When we are saying distributed data, it can be both centralized and decentralized. Decentralized is fine, right? We just were said that you can have mobiles collecting your data, and that is clear case of distributed decentralized data. But even in centralized setting, your data could be distributed. So, for example, suppose I have like 40 trillion tokens, and then in the morning it was said that only perhaps 2 billion, 1 billion parameter can make 40 gigabyte, right? 1 billion parameters, that also at half precision. So think about data when it is like in full precision, and then you have 1 trillion, right? So it is a billion in terms of trillion. So it is like several terabytes, right? So you just cannot have one system, one compute node storing entire data, right? So you would actually need multiple compute nodes even in a lab. So that's what happens in a supercomputer setting. So you have multiple systems fitted in a rack, right? And maybe they are connected with some network assisted storage, NAS, and so forth, right? And they have data distributed. So you could have centralized data you have already collected. So most of these LLMs which are trained, they are actually trained over centralized data, but in a distributed setting over a supercomputer. Okay. All these data centers, so to say, of big companies, they actually have that kind of machines, distributed data setup in a centralized setting. Okay, now again using our tool from mathematics, right? So please be comfortable with these notations, right? It is very simple. I have not used anything complicated. So our sort of gradient which was computed, right? We denoted, this is read as nabla, right? Those who have done mathematics. So this is nabla f. You can also call it the gradient f. Function is over your parameter and data, right? Data. So parameters state is being represented by this subscript little t, right? Little t denotes iteration number, right? And then this I denotes how many batches of data you have processed. Okay. So suppose you have n batches of data, then this is sort of in I goes from 1 to n. So this particular notation, this square bracket n essentially is this set 0, 1, 2, 3. Okay, this set is also denoted. Okay. Everyone fine with all the notations here? Yeah. So then you compute the gradient.
Sir, what is x t plus?
xt plus 1. Up to here is fine, right? Nabla if x subscript t comma bi, right? So we have picked a bunch of samples and then computed the gradient, and then sum it over all of those batches. That's the entire gradient. Okay, that's the entire gradient. And then this alpha was set as learning rate, right? Step size or learning rate, the dampening factor. And because you have like n batches, so average over it, right? So average over it. This average is required, right? We can prove it that without taking average, it cannot it will not be sort of proved correct. Okay. And then now what is happening is that this entire part is your gradient averaged and then dampened using the learning rate, and then you update your current model state x subscript t, and then the updated model state will be called x subscript t plus 1. So now you have moved from iteration t to from step t to t plus 1. So this is iteration t. In iteration t or iteration t, you are moving from state t x subscript t to x subscript t plus 1. So in first iteration, you move from x0 to x1. Okay, everyone fine? In the second iteration, x1 to x2, and this entire process. So this process is your now data parallel training, right? Data parallel training in a synchronous way. Why synchronous? So look, data parallel in the sense that we have these samples, right? These samples BIs being computed by multiple machines in parallel. Okay, so therefore parallelism is coming in data parallel. Every batch is being processed by one core, either on your laptop maybe, or maybe one node in a supercomputer set. Okay, and then you are summing them up together. And so unless you can sum them up together, you cannot take the next step. You cannot complete your iteration. So because you are waiting for all the cores to complete its task, therefore it is synchronous. So therefore synchronous data parallel. Everyone fine with the idea what I said? Synchronous data parallel. Data parallel because multiple cores are computing, and synchronous because unless the entire computation happens, you cannot take the next step.
Sir, so in general, a particular core generates random weights and pass it on to all the cores. They process different batches of data. Then they send back their loss functions and all that. And that same core initially who generated the random weights will now compute the gradient and again re-update it weights. So is this what's happening in the first iteration?
Very good question. Very good question. All right. So let me explain what is happening. So look, initially we started with the model state x subscript 0. Fine, everyone. X subscript 0. X subscript 0 is known to all the cores. Okay, known to all the cores, all the let's say processors, if it is processors, so to say, all the nodes, so to say, in a distributed setting. Now what will happen is that with that state x0, it will have, let's say core I will have its data set bi, right? A big B subscript I. Okay. What will happen? It will compute this particular quantity nabla f x0 comma bi. Okay, it will compute it.
Gradient for that batch. Gradient for that batch.
For that data batch. For data batch, right? But it is being computed at state x0 only. Okay, because x0 was communicated to all of them. Okay. Now once it has computed, similarly all the processors will compute, right? There are n processors because n batches, and this is data parallelism, so n processors. Okay. All of them have computed. All of them will exchange that computed quantities with each other, right? If it is shared memory setting, very simple, just go and write over the RAM what I have computed, isn't it? Everyone fine with that idea? So that's how computation happens, right? On your laptop or on a machine. So if processors do some computation over their registers and go and write it on the RAM, isn't it? If it is a distributed setting, multiple machines being connected with some network, then what will happen? Each of them will send their values to each other, right? That is called broadcast model in machine message passing interface MPI setting, right? And thereby what will happen? That each of them will have gradient computed by all their peers, right? Be it shared memory or be it distributed memory, right? Once they have it, they can then move further, do the summation, sum it up together, then do the averaging, done the averaging, then do what? minus subtract that from the state x0, and then you have thereby model state x1. Is that okay? Okay, good. Any other doubt? Okay, so so Professor Singh, so what should we do? It's
So
we should break, or should I continue for another 10 minutes and then we break at
10 minutes.
Okay.
To 4:15 we can.
4:15. Let's break at 4:15. So all of you are staying over the campus, or some of you have time constraint? But this is weekend. Everyone fine with that?
No, it's fine.
Okay, cool. So we'll break at 4:15, and I will be back maybe in 15-20 minutes. Okay? I will take maybe half an hour. All right. So you see, now we are again. Don't forget that now we are in the era of trillion parameter models, right? Trillion. Okay. So what will happen? Just exchanging this. First of all, forget your laptop. Forget even one machine. Forget even your NVIDIA DGX, right? Because it was already said by Anish Mukherjee in the morning that NVIDIA DGX is not sufficient. Okay. So what will happen? You will have multiple such machines, right? But still we are dealing with 1 trillion parameters. Okay. So what will happen that so this gradient that we have computed, right? So if your model, this model X, right? This model X belongs to 1 trillion dimensional real space, right? 1 trillion dimensional real space R to 1T. Then what will happen? Your gradient also, this nabla F also belong to the same space. The gradient has the same dimension as your function, right? So I hope either you have done it or maybe you do soon multivariable calculus in your engineering course, right? So in multivariable calculus, you know that this is a scalar valued vector function. This is a vector function, multivariable function. It is a scalar valued. For the sake of simplicity, here we are taking that the loss is at the end just a scalar, but it could be vector valued vector function. Okay, everyone fine with that? Okay. So our vector is 1 trillion dimensional. Every every dimension or every index takes how much memory size? 64 bit. If it is double, then it is 64 bit, essentially 8 bytes, right? So 1 trillion into 8, right? So 8 terabytes. Now think about it. So you have to communicate a gradient which is of size 1 terabyte. 8 terabytes, right? So it is just not possible. You see, in general, we have even in the setup of those big data centers and supercomputers, we have InfiniBand switches, so to say. And these days, those big InfiniBand switches are of capacity maybe sometimes even 100 gigabytes per second. So per second, you can transmit 100 gigabyte of data. Even if it is, let's say, 1000 gigabyte, 1 terabyte, still what will happen that you will have to communicate 8 times at least if it is like 8 terabyte, isn't it? So it's a big challenge, right? In the setting of even distributed machines, it's a big challenge. It's not as if that you just buy some NVIDIA DGX, right? A bunch of NVIDIA DGX paying some several thousand crores, and then you will be able to run it, right? You have to know how exactly you should do, right? So with that, what will happen? That you have to know that how to sort of communicate that big a gradient, right? That big a mathematical entity. So what we apply at these tricks, one is called gradient sparsification, right? Other is gradient compression. Compression is also called quantization, which the NVIDIA guy was mentioning in the morning. Compression or quantization. Sparsification, very simple idea. If you have like 1 trillion size parameter, just pick a bunch of 100 million parameters out of that, right? Leave others. If it is 100 million, now this is a tractable problem, right? So if it is 100 million, how much? Maybe 800 megabytes that you have to transmit, right? So it becomes a much smaller size data that you have to then send over the network, and then it works. However, you see, because we have just picked randomly, let's say this is one idea of sparsification called random sparsification. Okay, there are other methods of sparsification, but without going into that. So, so what you leave behind, that will create error in your training. Why? Because you were supposed to be using this entire gradient. Now you are using a gradient which is not exactly that. That is now lossy gradient, right? Now you have lost some part of it. So therefore, the this will create issue both theoretically as well as in practice. Okay. To deal with that, there is an idea called error feedback that I will just come. Similarly, compression or quantization, right? So it was said that instead of using full precision, use half precision, or now they are coming up with machines where you can just use 2 bits out of 64 bits. You can just use 2 bits, and that readily sort of downsizes your array, right, by 32, right, 1/32. Sometimes people also combine these two, sparsification and quantization together, and thereby you have a sort of efficient communication. Okay, everyone fine with what I am saying? That is system-based, perspective. So let me skip over this one, or maybe I can, without going into the detail of the notations, let me mention it. So what you could do, this is called local SGD, right? What you could do is that don't communicate the gradient for several steps. So just train the model over every core or every node for several steps, and instead of communicating it after every gradient computation, maybe communicate after 10 gradient computations. So thereby you can reduce your communication complexity, by as many local computation that you would do by that. So this is local SGD. Now I said that the problem was synchronous. Unless all of them would have done their task, you cannot finish your iteration. So an idea to overcome that is asynchronous. Okay. So what you do is that let those faster nodes proceed fast, and in slower nodes maybe do fewer computation. Okay. Again, what will happen, because you see with this kind of a model, this gradient which is being computed, you have now sort of newer notations introduced over J and T and so forth, right? This is actually again incorrect, or maybe not precisely the gradient that you would have needed to update your model. Okay, so there is some error here. It will create both theoretical issues as well as practical implications. Okay, what is practical implication? Before going into the theory, let me tell you that practical implication is that instead of maybe when you were in a synchronous setting, maybe if you were doing 100 iterations, right? Instead of doing 100 iterations here, now you will have to do maybe 110 iterations. But because this is asynchronous, a lot of data will be processed quite faster, because those faster nodes are given freedom to go ahead, right? And thereby even 105 iterations will take perhaps relatively a smaller time compared to even 100 iterations where you were being stuck. So imagine that situation when you are working with, let's say, I don't know, 50 nodes, right? And one of the node is just dead, right? It is stuck. And if you are in a synchronous model, you just cannot move ahead with your iteration. So therefore, synchronous is not suitable for this kind of training. Okay. So we apply asynchronous training. And federated I already talked about, right? I'm not going into the notations, but the idea is similar to local SGD, where you have multiple nodes. And then it was said in the morning, model parallelism. So model parallelism is that now you see even computing this one. So it was said that even with half precision you just cannot compute over one GPU. Then layer wise you compute over multiple GPUs. So each of the nodes actually contain multiple GPUs, and you compute one full gradient of your model using multiple GPUs. That is called model parallelism. Sometimes going beyond GPU, you actually apply multiple machines to compute one full gradient of your model, because it is trillion size and growing, right? And then sometimes you apply data and model parallelism together. So data parallelism we just talked about, that we have multiple machines computing gradient in a data parallel fashion. Now we have applied model parallelism inside every machine. So therefore data and model parallelism together, right? Multi GPU, multi node setting. And then sometimes even that is not sufficient, computing gradient of one layer. So we said that one neuron, several neurons stack to make one layer, right? And then several layers stack to make one deep network, right? now what we are saying is that even computing sort of gradient for one layer is not possible, right? So that we could have model parallelism. Even that is not possible. So what is possible? Now it is tensor parallelism. So one entire layer is expressed as tensor. Don't worry if you don't know what is tensor. Tensor is just a multi-dimensional matrix. Okay, so it is matrix multiplication. Tensor is just matrix, right? Several matrices stacked together. So this is tensor parallelism. So one layer's gradient is computed using several GPUs, and then even going further, now people apply data model tensor parallelism to it for bigger models. So that is the systems aspect of model training in big data setting, big data big model setting. I have some more stuff about its theory side and SDV and friends. So shall we break or? Okay.
Let's take a break.
Okay, so what about the audience? Should we break or should we continue for maybe? Huh? Let's continue, 15-20 minutes and then we break for the day. Yeah?
Yes. Actually, once you will have clear this part, then you will enjoy the hands-on session. The hands-on session.
So I have
They
one.
should
Do we have hands-on for today? Or it's already
Actually, today we have the basic. So after your lecture, we will do that for half an
Okay.
hour. We plan for shorter hands-on session for today.
Alright. Okay, let me finish. Okay, alright guys. So I hope it is clear that how exactly the training is happening. What is the mathematics behind it? What is the gradient descent? Right? Some people are not feeling too connected now with what is being done here.
Sir, I have this question. While you were talking about synchronous training, you said that we can also have delayed communication of gradients, like maybe after 10 iterations. So, like after the first iterations, each of those nodes, let's say there were 5 nodes who are having parallel computation in their own way.
Yes.
They had each of those had the x0 state with them. They got the data xi and they trained upon it. They got different batches basically.
Yes.
They trained upon it. They got their gradients now. Now we move on to the next 5 batches.
Mhm.
So like after the data set is exhausted, we are not communicating the gradients, right? Like we are waiting for whole 5 or 10 epochs to communicate those gradients.
Okay.
So won't the gradients be like moving in different directions, like?
Absolutely, very good, very good.
And how
question.
will we tackle that, or are we okay with that? Gradients moving in different directions.
Very good question. Very good question. Yeah. So that part, exactly that part, we are going to discuss in theory. Okay. So we are actually fine with moving in different directions. Under a certain bound, that it should not be too diverging. Okay. So that bound has to be maintained. So let me share my own experience of training the models in an asynchronous setting in a multi-GPU, multi-node cluster. Okay. So you will experience such things if you happen to be training machine learning models, that sometimes you run into NAND, right? So your model then shows NAND. So that happens precisely because of this reason. Sometimes what happens is that maybe even in a single GPU setting, or let's say a single node multi-GPU setting, if let's say some batch gradient computation became faulty, it will actually destroy the entire setup. Okay. So let's say in an asynchronous setting, when some GPU is faster, maybe it can compute up to some threshold. Okay, maybe 3-4 batches, but not beyond that. Not beyond that. If it becomes like 2 beyond that, then you will start seeing numbers instead. So how do you see whether it is converging or diverging? So okay, let me. So those curves are just here. Let me show it. Yeah. So, okay, I believe all of you have, those who have trained neural network, you have drawn these curves, right? Loss curve, right? Loss curves, it looks something like this, right? If it starts diverging, what will happen? You will actually see the loss curve, instead of going down, you will see the loss curve moving up. Okay, the training loss curve moving up. Once your training loss curve moves up in a distributed setting, just know that something bad has happened. either some communication has become too sparse, or maybe some node has become too slow, right? And thereby you should stop. And then I believe that those who have trained model, checkpointing, right? So you save that state of the model, and from there you restart. Okay. Otherwise it will diverge.
Yes, sir, but what I was asking was that 5 nodes, 5 different directions, they have now their gradients in 5 different directions. And now we have to take that gradient back after 10 iterations, let's say,
Yes.
and we have to then compute the average of that gradient.
Yes.
Now, if let's suppose the first 2 or 3 models are performing in the right direction, but 2 or 3 models have diverged. So now the whole average of the gradient will be in a diverging direction. So here the loss that we are actually getting will be a loss generated by the data only, but it won't be in the
In the correct
optimized direction.
Exactly
Yeah.
right. Yes.
So how will we know that okay, this is not in the optimized direction, because we actually don't know what the optimized loss is yet.
Exactly. So this is the theory for what you are saying. Okay. So we actually call it elastic consistency. So so I'm jumping ahead, in fact 2 ahead, right? But let me do it this way, because anyway we're short time. So let me answer any question that comes in, at any point. So look, what will happen is that, like you were saying, if you have let's say this gradient. So for example, this is being computed in this direction, the other one is being computed that direction, and this line is essentially its average. Let's say it is its average, right, which is moving. Now all we are saying is that as long as, let's say, this is the average direction, and this is the vectors, this vector, the gradient vector which is being computed, whose tip is here and its tip is there. As long as this distance, right, is under some bound, you can still hope that this average will lead you from the state x0 to your optimal state. Okay, and how would you know that? I just said that, just know that your curve should not go like that. Okay, so I mentioned 1 dB, or for that matter you can use any visualization tool for checking what is happening in your training, right? And then as soon as you see that your loss curve is sort of going in the wrong direction, stop. Checkpoint over there, and then restart from there, because it has already seen some amount of training, right? So your sort of that training investment should not go to waste.
Rearrange the batches that are being getting.
Shuffle it a bit, yeah. But even beyond that, look, so I would say that what was happening, your problem was not data dependent problem, it was actually the system dependent problem, right?
Yeah.
Because some machine had
because the
slow.
randomness of the weights that were taken, and then the difference of the data.
No. Beyond that, look. So some system. So system is not a programmer under programmer's control, right?
Yeah.
System's speed is sort of independent of everything, isn't it? So even if your data distribution was absolutely random shuffling had happened, right? But because some system became too fast or some system became too slow, therefore it was not under your control. So you don't even need to redistribute data. Just restart the process from there itself. It should work. But if you redistribute again, I mean, theoretically there is no change, because at the end it is just uniform sampling. Okay, does that answer your question?
Yeah.
Sir, how about we apply gradient clipping in that case?
Very good
if we
question.
would just remove
Very
the
good question.
possibility
Yes.
and-
Yes. So some of you who have trained these language models, you know what is gradient shooting and then gradient vanishing problem, and there we apply gradient clipping, right? So again, I mean, answer would be same, that if you see divergence, right, stop over there, checkpoint over there, the same idea. Yeah. So therefore, these ML ops tools are making a lot of money. They don't have to do anything. Actually, what happens when you train your model and you connect it to 1 dB? So there are several players in this domain. One is called Vex and Bias 1 dB. The other one is called Comet, right? So forth. So what happens is that they actually connect to your run either over PyTorch or TensorFlow, right? And then they show it on a browser-based tool that how your training is moving, right? I mean, I could have demonstrated it now, but anyway. So they can show it in runtime that how your running is